just collapses. I know, right?
Board comes down.
Take
And
out the
everything.
entire structure.
Yep. So here, Connor pointed this out. Did you guys see this yesterday? This is in China. There's a landslide took out that edge, that side of the bridge. They just opened it. Yeah, I believe that would be the Geotech's fault. Right? They didn't look at the
landslides come off the mountain.
Yeah, but even then, I feel like that would have been something that the geotechnical engineers should have been investigating and secured it and did what it needed to do to prevent that from happening. Unless there was an earthquake or something. Maybe there was an earthquake that did that. Does anybody know? Connor, did you listen to what? Maybe there's an earthquake that caused the landslide?
Sheer failure of the slope.
Whatever that means. I've never taken a geotech class. Yeah. I never have. Math, my undergrad degree was in math. Okay, so here we begin our second lecture on bridges. Okay, so we're gonna do that. So I'm hoping to have everything graded, right? You turned in the exam, your written part or the take-home part last night. Right? I haven't looked at them at all. Right? I'm through most of the exams at this point, of like the written exams, and then we'll go from there. I am still waiting on Neil. Neil has to take his take-home. Something about like I was playing the football game and recovering fumbles and shit. So, so he's gonna have it done. Did you guys see that? You got a big fumble recovery on that. Anyways,
We would have lost without that. It was a close one.
yeah, at the time, I will say, at the time it was still a little close, and I was just because they had a big breakaway. I was like, oh shit, and then somebody punched it out, and then they did it. Okay. Anyways, but then so probably on Friday we will go over everything. Okay. All right. So we got different types of bridges, structures below the deck, structures above the deck. Okay. And then structures at the deck. And these were already filled in for you. Floating bridges. We looked at this. You really only find these floating bridges. I just really like them in places where you don't have big tides. Right. And so in the University of Washington or near the University of Washington on Lake Washington in Seattle, they have the 520 bridge or 512 bridge, 520 bridge, and then I-90 cross Lake Washington. Otherwise, there's a big detour around them, and so they have these floating bridges, and they're super deep, and that's why it works there. But you don't find them in some places where there's tides because there's change of heights and stuff like that, and then ships and things like that. Okay, so what governs the type of bridge selection, right? These are my best. Were these filled in for you?
No.
Oh, maybe let's just use my completed notes. I don't have to write anything while you're going. What's that? No! Actually, this is very little writing anyway. I was looking through it, and we're just going to start looking at the code here shortly. So, what governs it, right? Economy, right? Economy, right? What's going to be the most expensive or not, right? The experience of the designer and contractors, right? Aesthetics. How does it look? How does it look like? How does it look like?
We speak good.
Yeah, we speak good, right? What does it look like? Because that is something that we do have to take into consideration. And actually, the code tells you have to be worrisome of aesthetics, right? We're engineers. We're not good. We ain't no good at that, right? On aesthetics, right? But the code, we'll look at it a little bit later. The code does try. It tries to lay out, like, this is what you need to do in terms of aesthetics. And an example of this, though, is in Kalispell, right? Or not Kalispell. I think it's right on the outskirts of Kalispell, like in Big Fork, I think. They had a big truss bridge that was there before that they needed to replace. And so then by default, they're just going to come in and put a girder bridge because they're very inexpensive, right? But they also are boring, right? And so that community pitched in to increase, like to get a fancier bridge out of it. And so they got a big truss bridge, like historic looking truss bridge. Even though it's brand new, they got it. But it's for the aesthetics to meet the requirements. Sometimes you see, sometimes aesthetics is simply like changing the color of the bridge. Have you ever seen when you're driving down like in southern Utah, a lot of like the overpasses and stuff are like kind of use the red dirt type of thing to like kind of match in with everything. So Public review, that's part of it. Constructability, speed of construction, right? So sometimes we have ABC again as accelerated bridge construction. That might govern it, and then what kind of spans that you can get out of it. So this is just I have a bridge design textbook, and this came out of that, right? These are the different span ranges that you might consider using these things, and also like the longest bridges, right? This one's crazy to me, right? 6,530 foot span. That's the clear span, right? Over a mile of a span. That seems unnatural, right? That just seems like maybe we shouldn't be doing that.
You should look up a picture of it.
I agree.
Not right now. I'm staying on.
That is on the
I know, but it's a delay. I gotta. Fine, fuckers. Akashi, right? Oh, don't look at that. Those are Connor's grades. Akashi, what?
It's right.
Whiskey.
Whiskey.
Holy shit. God damn. We should go street view all the way across.
I think that's a bridge, right? It is a giant bridge, right? As I said, I couldn't run across it. I'd have to take. I would have to take a break, several breaks, as I tried to run on that clear span.
Should look up the longest cable stayed bridge because they're cooler.
The what?
Longest cable stayed bridge because they're cooler.
I don't know. That's cool.
Would they have to put like a slip joint
No,
or
they're
something?
not.
Some people think they're
That's
ugly.
a personal offense.
Do they have to put a slip joint in there where the two cables come down in the middle?
Definitely asking the wrong person, Sean. Just because I'm teaching a class on bridges doesn't mean I know anything about them. I mean, really, what's going to do it? If you do go on, does anybody have interest in going to work at MDT? If you do, they're short like 25 positions right now in the bridge group in Helena, right? Whether that is something that is exciting to you or like, oh shit, like I'm going to be way overworked, right? I don't know. It's something to consider because they really are like, some of you might. I think it's a very steady job, very secure, right? I think you actually, in fact, are not allowed to work overtime. So like you literally, just by state law, you can't. So it's like 40, it's set 40 hours a week, right? You have a nice retirement plan, right? It's Helena. Yeah, so the old hometown there. Sometimes it's okay. Like now, honestly, I wouldn't mind living in Helena. It's very calm and quiet. Like you want to go out to eat breakfast, or you want to go eat breakfast in Helena, you just go out to eat. You don't have to like worry about big ass fucking lines that are. Right?
You get every
You guys-
holiday off.
What's that? You get all the holidays off. It's a thing to consider. If you're looking for a job, you can't find one stuff. Think about that. I think there's some absolute benefits to that, right? So, but I mean, really, what's going to happen is wherever you work, they're gonna teach you how to what do they usually design? What do they usually deal with, right? Some places in certain areas, maybe steel's way cheaper than it is in concrete, so they do all their steel design, their bridges. What we do mostly around here is the concrete pre-stressed girders is what we do, and so that's for most of the spans. We have 0 suspension bridges in Montana. There's a really cool bridge north of you even further, was it Medicine? It's on the outskirts of Glacier. There's a massive bridge there, a really tall one. That's probably one of our biggest bridges. Anyways, we don't have any of that. So I mean, it depends on where you're at and economy and stuff like that. So you'll do that. But this is just a general consider as you move forward, just so you can look at those, right? So Astro Electric Bridge Design Specifications, right, overview. So we're going to go, let me get back. Let me do the uncompleted notes. So we can fill it in here. All right, so this is the preface? The preface? Whatever. Whatever you want to call it.
It's the start.
The start, the beginning. This isn't this is the table of contents to the table of contents. That's what it is. That is literally what it is. It's the table of contents to the table of contents. I'm getting my notes. Hold on. Maybe I should have stuck with my completed notes. All right. So here's what the different chapters are. Right. Introduction, right? General design and location features, loads and load factors. So this stuff right here, right? This is kind of what you saw before, right? This is, like I said before, this is a massive document. One of the reasons it's a massive document is that it includes all of the material specifications and IBC and ASCE. It has all that stuff in there, but it also has in rules for the transportation engineer as well, right? So they have, some of the stuff won't even apply to us, like this general design and location features, right? Like, that's not us, right? Right? Transportation engineer deals with that. One of these videos that I think it was maybe one of those, there's one of those ones on the floating bridges. They interview somebody and they were like, oh, what do you do? It's like, I'm a transportation engineer. I do bridge designs. And then I'm just like, immediately, that's bullshit. You don't, right? The transportation engineer is not doing the designing of the bridges. The structural engineer that works with the transportation department is doing that. So the other thing with MDT, by the way, is there's lots of mobility. Like you start out in the bridge group and then work your way up to like the different heads of the different regions and then you can work your way up. One of our former grad students is actually the chief bridge engineer, Andon Collison. He graduated around the time Tim graduated, and he's the chief bridge engineer in Montana. And then also you could go lateral too. You could go over to different departments. You could be on geotech and water resources and things like that. I know, just in case you get tired of doing that. Okay, so this is where we're going to spend a lot of our time. Is this loads and load factors? Okay. This is what is new to us, right? You'll see, and I think I've said this before, right? What we focus on at MSU through all of our grad program is buildings, right? Like, I mean, even so much that even a class on bridges, we're spending 2 weeks talking about bridges, right? It is, but right? Like what we've taught you about buildings can then be transferred over and applied to bridges, right? There's just some modifications to it, right? And one of the big modifications is loads and load factors and the structural analysis evaluation, right? Those two things are different, right? But it's not that difficult. I mean, I think I asked James that, like, how did you make that transition? And he said it was fine, right? It's just different. And once you get in that realm, you'll see that they're very similar to each other. And so I stand behind we spend, and I should say most grad programs do that same thing. They focus on buildings with a little bit of bridges. That being said, they probably have a couple classes on specific just bridges. Although UW, where I did my master's and PhD, had no bridge class. And in fact, didn't even talk bridges at all, ever, right? So at least we spent 2 weeks discussing it, okay? These right here, right? Concrete structures, steel structures, aluminum structures, and wood structures, right? These are the different material codes. Material specifications, right? That's your AISC, that's your ACI, whatever aluminum is, right? In terms of their governing thing, and then wood structures, right? Your NDS is right. So you still use them. They refer to them like they're not gonna make up their own steel sections, right? They're gonna use the steel sections that are available, but like the governing specifications change slightly. Or sometimes they just adopt what AISC does. That's what they do with most of the concrete. It just adopts what ACI has going. But then they take that and put it in their own code, right? Those definitions are in there, right? So those are material specifications. We're not going to spend any time on that. And then we get into the rest of these things, right? Decks, foundations, abutments, buried structures, railings, joints and bearings. These are all components. I might as well stick to my coloring changes. Okay. Right. And these are right. We're missing Kira and Axel. Where's Kira? I'm gonna text her right now.
Text her and say she died.
I'm gonna text her too. Are you dead? Are you dead? What if she did? Now that's just.
Well, what if she responded?
Oh my god, good point. Where be you?
Maybe else.
See if she responds to either of us.
It says it delivered quietly.
Oh.
Oh, she read it.
Oh, she did. Oh, she's got read receipts on.
Not dead.
Don't do that.
What?
You shouldn't have read receipts on, right? Then you can't like snub people. Do you guys have read receipts on?
For some people. My
Or you could turn on just for certain people? Oh.
my phone doesn't do that.
I still don't want to do that. There's nobody I want to know. There's nobody that I want them to know that I've read their text and ignoring them, including my family. Especially my my wife texts me and I read it, then I don't.
Just knowing that, ignoring them.
Yeah. The plague.
What?
She's sick. Is that what she?
Yeah, she said she also has a plague.
Yeah. Okay. All right. That's bad. So I actually do have the exams. I was waiting for everybody. I'll hand them out.
Oh.
I do have it. It was a trick. I was waiting for Neil to show up so when we cover it, right, that we can go over it. All right, Neil.
Present.
We're gonna go over all of it. This is right. This is without the take-home part, right? The take-home part is gonna bump you by Ander. It was a trick. I got you. I got you.
Is it
Noah.
like 50-50 take home and
Yeah.
class?
No, I was gonna do 75-25.
In which direction?
75 on the written, 25 on the Tony. Gavin.
It's in the most recent series of
William.
previous-
You go by William or hey, me? Without looking.
I'll do Will, William, Bill, Dana.
Whatever you want. Thomas.
That's really not true.
Lucas.
A star?
Connor. That is a star.
Oh, how bad did I do?
Well,
Awful. Yeah, yeah.
Ciara. Oh, Ciara. Lucas. With you.
Why did you cross out the 7 and not write it?
Because I couldn't add. So that's something I would definitely look, right? Is to see Tim scribbled on yours.
Tim scribbled?
Yeah. You should make sure I added stuff up right. One time, Dawson, I handed back an exam and I left a whole page off when I added it up. And so he was like, he read it, he had a failing grade. And then he's just like, determined that he didn't. All right. Hudson. And then Allie. What do with access?
Did you get them all?
Did everybody get it? Okay, so let's go through these. Average was an 80. Average was an 80. High was a 98. Low was something in the mid 60s. Okay, don't panic if you're one of the ones in the mid 60s. Like you have the second part coming in, right? Hopefully you nailed the second part. You got the second part coming in. I think I I messed around with a couple of people's grades yesterday. It brings it up about 10 percentage points if you got everything right on the second part. Okay. Also, the bridges that exam is usually super easy. Okay, and so that also brings you up to get you by. Okay, so just don't panic yet. Don't not panic. But okay, so let's go through these things. All right, this one I think everybody did fine. Okay, what is the equation for it, right? And then the first is. I will also say this was a hard test. It was very difficult. It was specifically designed to tease out, did you know everything or did you not know everything? There were some tricky questions. We're going to get into that. I understand that they were tricky questions. I understand that they were hard. I understand that they could have gone multiple ways. And then that's fine. I was all part of it. I also gave in lots of freebies, right? Do you stretch the steel first before casting the concrete, right? Like that was supposed to be a freebie, right? Like there was another one that was there was another one. Oh, like we're just guessing, right? Like that was another. There was also 4 points of extra credit. There was matching of animals, which some people didn't do that great of matching animals. Neil, for God's sakes, man.
That's the first thing I wrote on my equation sheet.
It's Billings, man. Billings don't know their animals. I said, you got some of them right. I gave partial credit. I gave partial credit on the extra credit. Okay. That's all right. You did get the camel right. That was your suggestion. When you brought up camel, we should have known that maybe you didn't know your animals very well. We were talking about your fumble recovery earlier when you were here. That was sick. Yeah. Okay, so then that one everybody did fine. So I understand that, and then there is room for arguing back on some of these things when we get in there. So when we dive in, these ones are straightforward, right? There was the direct solve method, the tendon envelopes, the load balancing equivalent loads, right? And this one specifically said designing for allowable compression and tension stresses, right? I think there's a couple people that put in, the methods for calculating moment capacity, the ultimate moment capacity, but this one specifically said allowable compression and tension stresses. So direct solve, tendon envelope, load balancing, equivalent loads, computers, stuff like that. There was a very different. This one, all over the place, right? And this one was literally trying to just tease out, right? Do you understand what each of these load cases are doing? And then, that equation that you used, right, that we had and we checked all the stresses kind of was a combination of all of these things. But just independently, what do each of these load cases do, right? So the first one was the pre-compression. One thing I left out was the steel at the bottom. I think everybody understood that there was supposed to be pre-stressing steel at the bottom of this thing, right? And so with it at the bottom, you would have pre-compression that looks like this. Some of you sons of bitches drew compression on the left, and never in my life have I ever seen compression on the left. Every time.
I made sure to label it.
Yeah, you did. You labeled it. I didn't dock you for it. I was just like, who the fuck does this? Right? I wrote on there. It's like, but every stress diagram you ever drew in mechanics of materials and statics looked like that, and compression was on the right. Yeah. Okay.
They're right there.
And so in this one, right, I had compression to the right and tension to the left, like a normal person. Right, and so my compression would look like this because you'd have a component associated with the pre-compression, and then you would have a moment, a component associated with the popping it up part, right? The eccentricity, and so technically, if you really want to get into, that's what it should look like. I accepted anything basically. If you should, because I didn't say where the steel was, you could have made it concentric and just had it, pre-compression like that. Okay. Second one was the self-weight of the beam, is that right? The beam self-weight. In that case, right, it's just the beam, right? And it's going to cause compression at the top and tension down at the bottom, right? And so that one was fine, right? And it's just, again, separate load cases, right? So this is the pre-compression and then the self-weight. I didn't want you to add them on top of each other because the added on top would, be a hybrid between this one and this one. So I'm just that component, and I think most people got that. I think everybody got that. Next one was 3, the slab weight. So the slab weight, the only thing that's engaged when you put the slab on it is the beam, right? The slab isn't even carrying its own weight. So there should be nothing. There should be nothing up in the slab in this state right here, because at this point it's just all bearing on that beam. Okay. And then from there on out, right, it becomes a composite section, right? And you have stresses that look like this, right? You're going to have less stresses up at the tip, right? Because this is a lower strength concrete than this down here. And so then you'll have this little kink in there because you're transitioning between the two materials, right? If you really want to get picky, which I was, right? I docked you if you put those neutral axes in the same places, because really they won't be, right? Because the centroid will actually move up, right? It'll move up, and the bending will take place about that new centroid, right? Is where that's going to take place. So I was picky. I mean, I don't think anybody got all of it because I was picky on the moved neutral axis. Okay. That's it. That's all I was looking for. Not all I was looking there, but that really teased out. Did you understand the sequencing that was happening? At least I thought when you put a slab on top of it. Okay. Now these are the ones where you can maybe argue some stuff back. But this had to do with, right? Are they completely true? Are they completely false? And they might need an explanation, right? A, for example, right out of the get-go, needs an explanation, right? The ultimate moment capacity of pre-stressed concrete beam varies along its length. It's true or it's false. It would be true if your EP changes. If your pre-stressing is changing along its length. We didn't talk about that, right? We didn't bring that up. But like when you did your design, you did the moment capacity of your beam in the middle, right? But really, your moment capacity changes along the length because your location of your pre-stressing changes along the length. And so then your moment arms are changing and your moment capacity is changing as you go along the length. So technically, when you're calculating your capacities, you would have to check them at every location along the length because your EP, not only are your stresses changing, your elastic stresses, so is your ultimate moment capacity. That's changing as well, okay? And so, but if you had a constant EP, then it doesn't change. Right, and so then that would be the false, right? As the amount of pre-stressing in a beam is increased, the moment of inertia of the cross section increases, right? It actually does change, but we ignore it, right? And so then I don't know. So if you wrote false, but then put some, that's the other thing I did, by the way. If you put the right answer but gave me the wrong reason, I docked you. So it was just like, I was like, do you get it? Was it just a guess? Was it not? These shouldn't really be called true false. They should be like short answers, right? But some of them were straight up true or straight up false. You didn't need an explanation. But anyways, I went through and I read everybody's things and kind of teased out what was going on. And again, if you want to argue back on some of these, if you want to come at me, we can come at me, right? We can talk afterwards, right? So it's about pre-stressing. So technically it does change. We showed it changing, but we ignore it. And so what I was looking there was some little thing, yeah, true, but we do ignore it, or false because we ignore it, or something like that, right? Miscalculating pre-stress losses can cause life safety issues, right? We talked about not really Breaking Bad, but then if you're talking about shear capacity, maybe eventually if you're so far off. I think the statement that we had in there was, not really, but maybe, I think is what it was. And so, and what I did, what did you say? Well, we can talk afterwards. We'll talk afterwards, Kyle. We'll talk afterwards. Because keep in mind, when I was grading these, I was also drinking. So they might not have been consistent, right? You want to be near the end of the pile, right? When I'm grading, because I'm a happy drunk. I'm not an angry drunk. My wife's an angry drunk. Well, myself, I just get whatever. This is awesome. We're all doing concrete. This is great. Okay. All right, but if you said, oh, true, because it affects shear capacity, or, remember Breaking Bad, like you lose your job because your pre-stress losses and you got extra cracks, and so then you start selling crack, and then you're like, right, How many of you somewhere upgraded your calculator from like an old one to a new one? Did you ever regret that, Thomas? Did you go to like a TI-89 and then, right? Anybody in here who all upgraded your calculator? What? Just
Like downgraded.
you did, Tony?
Yeah.
You're the only person I've ever met that didn't like their ICER calculator. Anyways.
Being able to solve integrals during an exam is
Yes.
fantastic.
Yes.
Well,
And then using matrices, so because I preach in dynamics. Those I preach like get an 89, get an 89, get a 99.
Directly tell everyone in the MLC that that's bullshit.
It's not bullshit. You guys,
I don't know how to use it.
that's the problem. They don't know how to use it. But if they take the time to learn how to use it,
And also
so much better.
many people say, oh, my calculator just can't do it. And I'm like, your calculator actually can. You just
Yeah.
are saying that it's not as good.
What I've thought about doing in ECA is well, I can't require people to get the TI-89 in dynamics, but I can at least show them how to do some of the stuff, just to show them that their calculators have the capacity to do like matrices and things like that, and actually show them in class. Anyways,
That would be good. I think that a lot of people think that there are calculators that aren't shitty calculators, like TI-84s and stuff. I think people think that they can't do anything with
Yeah.
them, but they can. I feel like they think that
yeah,
you can only do stuff with the 89.
right, but they also suck, 84s. But
But they can do a lot more than people think.
you're right, absolutely, and they never learned how to do it.
And they're
Yep.
like, oh yeah, they can't do anything.
In my undergrad, they taught us in the math class how to use those calculators and do all of those things that we talked about, which I thought was great. And then here, they don't even let you use calculators, which is stupid, right? It's so stupid. It's so stupid. Okay, then back to this. Typically assumed to be negative effect test stressors actually decrease. Oh yeah, okay. So this is typically assumed. This one was this was actually straight true or straight false, right? And this one in case was false because what I got you with was right. Typically assumed to be negative effect. The tendon stress and flexion will actually they increase, right? They increase, don't decrease, right? And so in that case, that one is just straight false. You're fine with putting straight false. Okay? Increasing the allowable stress at a transfer in pre-stressed concrete beams will increase the service load carrying capacity, right? It actually doesn't do anything to your service load carrying capacity, but it does let you move the tendon, right? So, because remember what's happening is you got the envelopes to go and say you got to stay below this, another thing saying you got to stay above that. By increasing that allowable thing, it lets you move it down. So it lets you move it down. So I accepted true there if you said, oh, it'll let me move my tendon down and therefore my capacity will go up, right? That was fine, okay? And again, I know that some of these are kind of being nitpicky, but that was the point, was to kind of tease out of this, right? Using crack section properties and deflection calculations will account for long-term, that's completely false, right? Those are two different things. One is cracked stuff happens immediately, right? And crack section it's just a completely different thing. The long-term effects are creep and shrinkage and things like that are affecting your long-term deflection. So don't just do the cracking. Okay, and that actually, I got that question because I had a colleague of mine that did pre-stress design, and I said, how do you account for long-term deflections? He goes, oh, I turn on crack section properties. And I was like, oh, fuck. Right? Like, that's not, those are completely separate, right? And anyways, so the dangers of just doing that stuff. Okay, if a pre-stressed beam is to have an issue with shear, it'll most likely occur at the ends of the beam. No, because that's where your capacity is also higher, so that's false. It's somewhere in between. I think everybody got that one right. During construction of precast tension, remember, you should stretch the tensions prior to casting the concrete around them. Otherwise, you're getting some weird shit, right? If you cast the concrete and then stretch it afterwards, you're just going to get a bunch of tension cracks along the whole thing, right? So that was kind of a joke. Okay, generally speaking, concrete design, discussing that, it's just all a guess. We're just guessing. We have no idea. It's an educated guess, but it is a guess, right? Whereas steel is just, I agree with Tim. There's some cool things about steel. It's just because he likes it so much because he doesn't have the mental capacity to deal with concrete and how complicated it is, okay? So this one, the debonding on the ends, right? The reason for the debonding on the end has to do with the fact that you have, less external moment, less self-weight moment near the ends, so you don't have anything to counter the pop-up, right? You got, this is what's pushing it down, this goes to zero, this is my pop-up, right? The eccentricity from the pre-stressing causing it to pop up, and so we debond it near the ends right here so that this doesn't exceed this and we get tension failures, right? And so by debonding it, we save from cracks happening at the top at this location. So in order to get the full credit here, you had to say something about your moments, your external moments being near zero near the ends. right? You had to say something about that. You can't just say, oh, to prevent cracks. It was like, well, why does it happen there and not anywhere else, right? The reason it happens near the ends is because of this, right? When checking
What
the,
did you imply mechanically? You just said why.
what's that?
I'm arguing for myself here. You just said why does that happen? You just said why does this happen mechanically?
Why would you do it? To prevent
But you
cracks?
can have-
Why would you do it?
To prevent
You
cracks.
asked specifically
Well,
why.
yeah, but
But you didn't ask.
But
why
there's part of
mechanically you
the
do
part
this.
of the why. The part of the why is the moments are not are zero near the end. That's part of the why. You just didn't have a complete why. You had part of a why. I wanted all the why.
How would I
Why?
want that in front?
That's right.
I
Why would you do this? Well, yeah, you could almost say prevent cracking for almost everything pre-stress related. But anyways. Okay. All right, this one, right? Again, this is one that you had, right? Absolutely. To prevent a brittle failure. Right? Great. Right? Great. That's if you said that to prevent a brittle failure, and then to fix it, you add in tension reinforcement, not pre-stressing. Because if you add pre-stressing, then it increases your moment capacity and it increases your cracking capacity. But if you just put in regular steel, it only affects the other one. That being said, in order to get the full credit, which no one did, which I just proved to myself that nobody understood what was happening, is I wanted a little explanation of why does it avoid the brittle failure. And it has to do with, right, everything looks great, beautiful, everything's great, and then if you overload it, a crack forms. And as soon as that crack forms, the mechanics switch from this to this, right? And if this capacity isn't big enough, then it just comes crumbling to the ground immediately, right? I wanted something like that. I wanted something, do you get why? Like, I understand the brittle, great. I think I just took 1 point off if you didn't say something about the mechanics switch from this to this, and if we don't have enough steel in here in this capacity, and this capacity is less than this capacity, then you get a brittle failure, right? I wanted something like that. I wanted it, but I didn't get it, which
The
means that
requirement is in place to avoid a brittle failure. That's
correct.
the whole why it's there. You
I
don't
mean, I'll
have
add in,
to
I'm going to start
brittle
at,
failure.
next time I'll say, completely explain this requirement,
Like,
right?
The code only
In
requires
more
it 'cause we don't
depth.
want a brittle failure.
I know, but
That's
I
why it's
told
there.
you why. But I told you why. I told you why.
But you didn't ask.
I did ask right there.
Yeah, and it's in place. to
Well, I'm
avoid
just
brittle
saying.
failure.
Just saying. I can have my wish list. That's what I wanted, right? Pros and cons. I think everybody got this one fine. Light, slender, durable, improved deflections, cost, no gain, and ultimate strength, has brittle failure mechanisms, things like that. I think everybody did find that one, right? Oh, man. This is, yeah, whoa. This is another one that I wanted, and I think like 3 of you got this one, at least close at least, right? So what this had to do with, and I think it's a fair question because we did one like this and had the diagrams in the thing that showed it, right? And the problem is this is statically indeterminate, right? Statically indeterminate. And so you have a primary moment, a secondary moment, or hyperstatic moment, and then you have a combination between the two, okay? So what it is, right, the way we did this in class is you remove one of those constraints, right? One of those constraints would be this, right? Because this thing wants to curl up. Right? It wants to curl up because the eccentricity, my pre-stressing strand is at the top, right? And so it wants to curl. And it's causing a constant moment. And that constant moment is FP times EP, right? That is that constant moment because the EP is constant along the whole length, and then you have FP times that, so FP times EP, right? And so that is causing a positive moment, right? The reason it's a positive moment is because you're getting squishing at the top and pull apart at the bottom, right? Tension on the bottom. So that's a positive moment. So what your primary moment is, it's coming from your pre-stressing strand. So it's a constant moment along the entire length, okay? To think about the secondary moment is that this sucker wants to curl up. And so what I do is I remove this thing right here and then it can't curl up because there's a downward force there. And so then you analyze this as a cantilever with a point load coming down because there is going to be reaction there. Because the thing wants to curl up, there's going to be a reaction that pushes it back down. And then that would be the moment diagram from just a point load over on the end. right? Because that's the secondary moment. That's because it can't pop up, and so there has to be reaction over there, and that causes that moment right there, right? And so it starts out, it's a negative moment because we are pushing down, and we're getting compression in the bottom and tension up at the top, and so then the combination of the two, it actually turns out that it's here. It's 0 on the end and the moment over here, like I said. That being said, if you didn't know that this was equal to this, you wouldn't know that. So any kind of line that like that with these two added together, maybe not known magnitudes, I accepted that. Definitely not, something that like this. Definitely not some people got like these for the, that's just random, right? That's it. That's all it is, right? And again, I do think this one was fair. I did show you this one. I did we did an example like this. We talked about how to pop it up and then get back down, right? That being said, it was fine. And I think I gave, if you drew lines, I think I gave points. Right? I think that's what you said. Maybe not if your lines were all completely wrong. I don't know. I don't remember what I did there. But come in and talk to me if you want to. Okay. This was a journey, this one. This was a journey. Yeah. Okay. This one I think this one really did tease out some stuff. Okay. As a transverse, so again, you put an increase, decrease, or stays the same, right? As the transverse load applied to a pre-stressed concrete member is increased, the internal compression resultant C in a moment resisting couple acting in the member, it stays the same. And we had a little comparison between reinforced concrete and pre-stressed concrete, and we said in pre-stressed concrete, C and T stay the same, but then their moment arms change. In regular reinforced concrete, C and T get bigger and smaller. That's what I was referring to. Right, so the C would stay the same in pre-stressed concrete because it's coming mostly from the big pre-compression force that's there no matter how much load is applied to it. Okay, increasing the pre-stressing force, FPE, will generally result in an increase in the shear capacity. So that was your Moore circle arguments and stuff like that. So it increases the shear capacity. For a given pre-stressed cross-section, increasing the span length will do nothing to the nominal moment capacity, right? One's on the demand side, one's on the capacity side, right? So that's why that one stays the same. The span length has to do with demand. Capacity is independent of the demand, right? And so that one stays the same. Sysidus was the answer. Sysidus, right? That's how I graded it, right? As the eccentricity of the pre-stressing tendon increases, moving from the end of the, so these were like, right? You have to think about this shit, right? As the eccentricity of pre-stressing tendon increases, moving from the end to the center span, the axial stress at the center of gravity of the cross-section stays the same. Because all of those stresses, go back to that original stress equation, it's all M over S, right? FPEP over S. All that bending is taking place about the CGC. So any moment you apply to it, all that's taking place about the CGC. So that doesn't change it at all. The only thing that's affecting the centroid is the P over A. So no matter where you're at along the whole length, P over A is what your stress is in the middle. Okay? That's why that one stays the same. All right, that was that one. Okay, at lower relative humidities, the loss of pre-stressing would be expected to increase. This one was like at lower relative humidities, you'll get more losses, which means your loss of pre-stressing will increase, right? And so there's I think some people got hung up on you get more losses versus, or your stresses after the losses would decrease, so anyways, that was the increase, right? This one right here, right? This one's a tough one. As the magnitude of live load increases, the distance from the bottom of the beam cross-section to the tension tendon envelope on the top would what in magnitude, right? So what I was looking for, right, and this is where I tried to clear up the wording. It used to say, on an older exam, it used to say the upper tension tendon envelope. And so some people thought of the envelope that controls tension at the top, okay, of the cross section. But I'm talking about the tendon envelope that's on the top, which controls tension on the bottom, is what I was looking for. All right, and that's why I try to say the tension tendon envelope on the top. So these are what they would look like, right, going across. So this one, the tension bottom at service would be this one, right? And then this one right here would be the one staying above. This one's associated with the tension at the top. This one's associated with tension at the bottom, but it's the line that's on the top, is what I was looking for, okay? And so my thing was, if I increase the load on this, what is it gonna do to this one? It's gonna move it down, right? It's gonna say you have to stay below this, because if you're below this, you're gonna get less tension at the bottom, and so then that's where you're gonna fix it. So that one, that's why that distance decreases, right? Is that distance from here to here, right? And that's gonna go down, which means that the distance in between those is gonna decrease. So the answer there was looking for decrease. If in your heart of hearts, in your mind, you were thinking tension at the top, and you wrote an increase on there, then I don't think you get it anyway, because increasing the load, it would stay the same. It would stay the same. It would stay the same. Is that what you were thinking in your heart of hearts, Luke?
Yeah.
Then I'll give you credit for it, okay? Because I next time I do this, I'm going to say the line on the top, motherfuckers, right? And then do this. You're gonna try. What's that?
Draw the diagram. That one
And
right.
point at the line you're talking about.
Envelope.
Yeah, I'll say, yeah. What does this line do? I like it because you really have to dig in deep. You really do. You have to dig in deep. There's so much involved with that one question. Okay? In a PT floor design, the amount of pre-compression of the slab should be increased. Kyle said that in passing in one of his lectures, right? He was saying that like when you're doing a garage, for instance, you increase your pre-compression force because you're going to have more exposure to the elements. You want to keep the cracks even tighter and stuff like that. So that was an increase. For a given pre-stressed concrete beam with composite topping, stresses in the beam due to pre-stressing will stay the same if the slab is short. Because the pre-stressing is independent of any other loads that are happening there. You just put the pre-stressing on immediately and then that's locked in. It has nothing to do with what you put on top of it or anything else like that. That was a trick.
So you're saying like you pre-stress it and then that force doesn't change?
No.
I thought you were talking about
Due to the
design
pre-stressing.
Pre-stressing form.
Beam due to the pre-stressing. Due to
Yeah,
the
but
pre-stressing.
the design pre-stressing form could.
Oh, if you dug in
Yeah.
deep, if you
Yeah.
dug in deep.
That's what I thought.
I thought you were
That's
talking
what I thought
about,
you were talking about.
Like, when you
Okay,
add
Okay, right?
once
I'm
you add-
accepting it. If you're not just copying him.
No.
All right? Yeah, I'll accept that too. If you were thinking, well, I would change the design and then I would increase the thing, fair enough. I'll give you that one, right? I'll give you that one. I'm fair. I'm benevolent. Okay. Do you guys have a second? I know we're 3 minutes over. I'll finish it up. Right. 0.6, right? 0.6 F prime C is the stress limit. 7.5 squared F prime C is the concrete cracks. Okay, that's an assumption in a couple different places. That's your rupture modulus. It's a limit between uncracked and cracked. 0.003 is the ultimate crushing strain in concrete. 7 is 7 wires in a tendon, in a 7-wire tendon. I think, Will, you wrote 7 strands in a strand, but that's okay. I'll give you that. I knew what you meant. Right. 33. Okay. I'm accepting 33 kips in a pre-stressed tendon. Right. I'm going to give you that one. I didn't at first. I tried to correct it. Might have been on the fly that I did the correction. So if I did mark you off for saying 33 kips, then it's because Axel kept saying 33, and then I missed Kyle saying 33. That's one of them. So it's kips in PT tendon when you start out. That's how much you stress it to. That's how much you stress it to before you release it on the anchor. Or it's 33 times the weight of your concrete in PCF to the 1.5. And so some people saw that. That's another way for calculating elastic modulus. Right? In which if you put in normal weight concrete, you get 57,000 for that number. That's where that 57,000 came from, putting in 150 right here, right? Or 145 or something like that. So 0.65 is the fee for compression controlled sections for flexure. 0.85 is your Whitney stress block, or it's the beta 1. I accepted either one of those. 0.153 is the area of a 1/2-inch PT tendon. 0.9 is your fee factor for tension controlled members. 57,000 is used for calculating the elastic modulus. 0.005 is the strain in the steel, right? It's the strain in the steel that governs whether or not you can, or it's the border on this 0.9. Otherwise, it's the transition. So you hit 0.005, your fee factor is 0.9, okay? 270 is 270 KSI steel. 318 is the committee. This 318, 19, I think, is the current code that we use. 26.8 is the assumed force in the PT tendon after losses. It's your F effective. or P effective, depending on which variable you're using, right? So you start out with 33, but then when you actually design, it's 26.8. Okay, this is Stanton, right? That's in one of his notes is where the picture of himself. There was the journal article on sign convention had a picture of him. That's a Mangel diagram, right? We don't use those things anymore. And then this is a seal. This is a sea lion. This is an alpaca. This is a llama. This is a black bear. This is a grizzly bear. That's a wolf. That's a coyote. And this is the seal versus, when I see him, ChatGPT, I got to do this. It did all these for me, right? It did a pretty good job. I think it exaggerated the differences between them, but I thought this was a journey. This was a journey to get Chat to do this. It was quite the journey.
I was convinced you were going to do a similar like that. Or like a Brad.
Oh, I should have done that. Yeah, I should have done that. So Neil, this is a llama, this is an alpaca, this is a camel, this is a sea lion, this is a seal, this is a coyote, right? This is a black bear because it's black. This is a grizzly bear because it's... And then
I got the bears and camels.
the bears and camels. You got, yeah. Febsigna is how I graded that one. There was a couple. You weren't alone, Neil. You weren't alone.
The coyote looks smaller than the wolf in that.
Yeah, but look at the face, the pointy ears, the narrow face.
That's not a Montana wolf, Mike.
No, it's not. That's not. Coloring.
Okay, Sean.
John's not throwing shit at you, Neil. Not throwing shit. Yeah. But now I look at him, and clearly there's a difference. Like, who would ever mistake this and this? Right? For God's besides Neil, right? They are completely different, right? Like, this I could club, this I couldn't club, right? Don't they do that, right? Like club baby seals, that a thing, right? That's what?
Yeah, no, you're right.
I do, right? That's a
thing.
That's a thing, right? That we did. Like, we went out and clubbed a bunch of baby seal and then made coats out of them. Maybe not we. Yeah. All right, I'll show you. On Friday, I'll show you the journey that me and Chat went on to try to get these pictures. It made some interesting animals. It was like combining them and shit. Like it was weird. So, all right, sounds good. Thanks, guys. If you want, we could talk right after this. We go down and thing we can talk about. Oh yeah, that's the other thing. I have to have those. I haven't recorded them at all. So if you don't give them back to me, then you don't get a grade.
If I'm coming to argue with you, should I just hold on to it?
I specifically did that on purpose. Do. We'll go. I specifically did it on purpose where I did not record them. So if you want a grade, you gotta give them back.
Do you know if there's a range that like
It's low on our priority because they'll just add to stuff. But I'll get to it. I was honestly on it until I'll get to it. Yeah, sorry, my bad. Keep on me though. Keep asking because you don't want me to not do it at all. So.
Did you estimate?
yes.
Okay.
That one, this one, and
I'll look at your other stuff after this. I think
You think?
yeah. One thing we could do, Allie, and I'd be fine with this, is
That doesn't smell like
because you still have the
Check
biggest
spelling
thing that I
here.
have with is
I mean, if
This
it
is
is
too old.
true,
Right.
it's killing.
So let's just if I just extended that, right?
Yeah.
And then just do a really good job on it in the next couple weeks. Let's
It's
just
been a long time.
okay. And then now bring that up. This I wouldn't worry about this because you add in this with the take home. Hopefully, you did fine on the take home.
Because at
And
first
then with the take home, and then the other exam.
And then I
I
realized
think
it
you'll be
was
fine.
And then the other thing I was
pre-stressing.
gonna ask about.
And then I realized
was,
pre-stressing
like,
was at the
on
top of the beam.
syllabus,
Yeah.
and the different breakdown.
I like vaguely remembered. I was like, is this
So how is the actual?
My plan is to do the breakdown the way it's on the syllabus, and I think that what
So like the final is gonna be worth more than what it is currently on the campus.
what is it worth?
On the canvas, I think it's 20,
Did you
and
get all your
on the
answers?
syllabus, it's still 30. Like it's still pretty equal with the homeworks.
Okay,
and-
let me look at it.
It's
and
really
I'll get
funny
back
for
to
Okay,
you.
because I think
Yeah.
that would also.
Yeah, I think because it just imported in my grading from last time I taught it in a weird way, and so like,
So it was like
because it went from D2L to
45,
Canvas, yeah.
20 and 10 on Canvas, and then in the syllabus it's 30, 30, 30, and 10.
Okay, okay, I'll look at that too.
Okay,
Yeah,
you think that's gonna be?
I think it'll be fine.
Okay.
Yep, I think it'll be fine.